the ancient storms that reshaped an entire planet. Long before Mars became silent, it was ruled by chaos in the sky. Storms so vast and persistent that they altered the fate of an entire world, not in days or weeks, but over ages. These were not transient weather events, but sustained atmospheric upheavals that operated on geological timescales, fundamentally transforming the planet's climate, surface, and capacity to sustain complex systems. The storms of ancient Mars were not merely meteorological phenomena. They were evolutionary forces that shaped the planet's trajectory from potentially habitable to definitively barren. To understand why these ancient storms matter today, we have to imagine Mars as it once was. A planet with air thick enough to move weather, temperatures warm enough to sustain cycles, and energy strong enough to drive violence across the surface. Mars was not always calm. It was once aggressive. Early in its history, Mars possessed an atmosphere several times denser than today's, perhaps approaching Earth-like pressure in some models. This thicker atmosphere could retain heat, drive wind systems, support clouds, and possibly maintain liquid water on the surface. The planet was warmer, wetter, and dynamically active, a world where atmospheric processes could sculpt landscapes and influence geological evolution. Early Mars experienced extreme atmospheric activity. With a thinner gravity and a young, unstable climate, wind became a dominant force. Dust did not merely drift. It traveled. It accumulated. It reshaped landscapes slowly but relentlessly. Storms lasted not hours, but seasons. Mars's lower gravity, about 38% of Earth's, meant that particles once lofted into the atmosphere stayed aloft longer and traveled farther before settling. Wind speeds that would be moderate on Earth became powerful on Mars, capable of mobilizing vast quantities of fine dust. Once initiated, dust storms could persist for months, their duration limited only by the depletion of atmospheric energy or changes in seasonal forcing. The scale was planetary, dwarfing terrestrial storms both in extent and endurance. These storms fed on imbalance. Temperature differences between hemispheres grew stronger as Mars lost stability. Winds accelerated. Dust lifted higher into the atmosphere, blocking sunlight and cooling the surface further. Each storm reinforced the conditions that created the next. This positive feedback mechanism was fundamental to Mars's atmospheric evolution. As the planet's climate destabilized, perhaps due to declining volcanic outgassing, atmospheric escape to space, or orbital variations, temperature gradients sharpened. Strong gradients drove powerful winds. Winds raised dust that absorbed solar radiation aloft while shading the surface, amplifying thermal contrasts. The system became self-reinforcing, each storm priming conditions for subsequent ones. Unlike Earth, Mars had no oceans to absorb energy, no forests to slow wind, no rain cycles to clear the air. Once dust entered the atmosphere, it stayed there, heating the upper layers while freezing the ground below. Mars's climate became trapped in feedback loops it could not escape. Earth's buffering systems, vast water bodies that moderate temperature extremes, vegetation that stabilizes soil, precipitation that cleanses the atmosphere, were absent or minimal on Mars. Without these regulatory mechanisms, Mars's atmosphere responded more dramatically to perturbations. Dust once airborne remained suspended for extended periods, creating a semi-permanent haze that fundamentally altered the planet's radiation balance. The upper atmosphere warmed from absorbed sunlight while the surface cooled in perpetual twilight, inverting the normal temperature structure and further disrupting circulation patterns. Over time, these storms did more than move dust. They altered heat distribution. They accelerated atmospheric loss. They stripped the planet of resilience. Mars was being reshaped not by a single catastrophe, but by repeated stress. The cumulative effects were profound. Dust storms redistributed material across the surface, burying some features and exposing others. They modified albedo patterns, changing how different regions absorbed or reflected sunlight. They heated the upper atmosphere, allowing lighter gases to escape to space more readily. They eroded surface features through sustained wind abrasion. Each storm cycle left Mars slightly changed, and over millions of years these incremental modifications accumulated into fundamental transformation. What makes these storms ancient is not just their age, but their influence. They were not symptoms of decline. They were drivers of it, and their legacy is written into every barren plain and eroded ridge we see today. The storms were active agents in Mars's transformation, not passive consequences of other changes. They accelerated processes that might otherwise have proceeded more slowly. They established feedback loops that became difficult to break. The Martian landscape we observe, wind-sculpted yardongs, dust-mantled plains, stripped hillsides, testifies to billions of years of wind action driven by these ancient atmospheric disturbances. Mars did not fall apart quietly at first. It was worn down by the sky itself. The planet's decline was not gentle entropy but active degradation, with the atmosphere serving as both victim and perpetrator of environmental collapse. As Mars's atmosphere thinned, storms became both symptom and accelerator. With less air to regulate pressure, winds moved faster. With less moisture to bind particles, dust lifted more easily. Each change made the next storm stronger than the last. This created a destructive spiral where atmospheric loss enabled more aggressive storms, which in turn promoted further atmospheric loss. Thinner air meant lower pressure gradients were needed to generate high wind speeds. Drier conditions meant dust particles lacked the cohesive moisture films that help bind them on Earth. The combination made Mars's surface increasingly vulnerable to wind mobilization even as the absolute energy in the atmosphere decreased. These ancient storms did not simply cover the planet. They interacted with its chemistry. Dust carried iron oxides, darkening the surface and altering how heat was absorbed. Some regions warmed, others cooled. Climate contrasts intensified. Stability slipped further away. The dust was not inert but chemically active, carrying minerals that modified surface properties were deposited. Iron oxides gave Mars its characteristic red color, while simultaneously changing the surface energy balance. Darker, dust-covered regions absorbed more sunlight and warmed relative to cleaner surfaces, creating thermal contrast that drove local circulation patterns. These circulation patterns, in turn, influenced where dust was deposited and eroded, creating complex feedback between surface properties and atmospheric dynamics. Global storms likely became seasonal events. Entire hemispheres disappeared beneath dust clouds for extended periods. Sunlight struggled to reach the ground. Surface temperatures dropped. Any remaining liquid water became harder to sustain. Mars's climate systems weakened with every cycle. Orbital mechanics and seasonal variations in solar heating created periodic triggers for major dust events. When Mars reached perihelion during southern hemisphere summer, the intense solar heating created strong temperature gradients that launched dust storms. Once initiated, these storms could spread globally within weeks, shrouding the entire planet in an ochre haze that persisted for months. During these events, surface conditions became extreme, near freezing temperatures even at midday, perpetual dim light, and atmospheric conditions hostile to stability of any kind. Storms also affected atmospheric escape. Dust heated the upper atmosphere, allowing gases to drift into space more easily. This slow leak compounded over millions of years. Mars was losing air not through explosion, but through constant agitation. When dust absorbed solar radiation in the upper atmosphere, it heated surrounding gas molecules, increasing their kinetic energy. Some molecules gained sufficient velocity to escape Mars's weak gravitational hold entirely. Others were stripped away by interaction with solar wind, a process enhanced by the temperature increase. Over geological time, this mechanism contributed significantly to atmospheric loss. Mars did not lose its atmosphere in a single dramatic event, but shed it gradually through countless heating cycles driven by dust storms. The planet lacked recovery mechanisms. Earth storms end. Rain clears the sky. Oceans moderate extremes. Mars had none of these buffers. Once dust dominated the atmosphere, it remained dominant. On Earth, precipitation acts as an efficient atmospheric cleansing mechanism, removing particulates and resetting the system to clarity. Mars, with its minimal water vapor and low temperatures, rarely if ever experienced precipitation capable of clearing the atmosphere. Without this reset mechanism, dust accumulated over successive storms, creating a semi-permanent atmospheric burden that never fully cleared. The system had no way to return to a clean baseline state. These processes reshaped the planet unevenly. Some regions were scoured clean, Others were buried beneath layers of sediment. Geological diversity increased, but habitability decreased. Mars became more complex and less alive at the same time. Wind patterns concentrated erosion in some areas while depositing thick dust mantles in others. Highlands were stripped to bedrock in places. Lowlands accumulated layered deposits meters to tens of meters thick. The result was a heterogeneous surface where adjacent regions might differ dramatically in their modification history. This complexity makes Mars fascinating geologically, but also documents the progressive uninhabitability. Regions became more extreme, more variable, less conducive to stable conditions. Understanding these storms reframes Mars's history. They were not isolated events. They were part of a long decline driven by instability. The sky itself became an agent of erosion. Storms were not discrete episodes punctuating otherwise stable periods, but rather the dominant mode of atmospheric behavior during Mars's transition from habitable to hostile. The atmosphere did not merely weather decline. It actively participated in it, serving as a medium through which energy imbalances manifested as material transport, chemical modification, and progressive degradation of surface conditions. Mars did not lose its atmosphere all at once. It was shaken loose, storm by storm. Each dust event contributed incrementally to the long-term loss, heating the upper atmosphere and facilitating escape, stripping gases particle by particle across billions of years. The conflict created by these ancient storms lies in their persistence. Storms are expected to pass. On Mars, they became a condition rather than an event. This transformed temporary weather into permanent climate state, a shift that fundamentally altered the planet's trajectory. When storms are episodic, systems can recover between events. When storms become chronic, recovery becomes impossible and degradation accumulates without respite. As the climate destabilized, Mars entered a cycle where storms fed decline, and decline fed storms. Each dust surge reduced surface warmth. Reduced warmth weakened atmospheric circulation. Weaker circulation made the system more fragile. Fragility allowed larger storms to form. This self-reinforcing cycle had no natural breaking point within Mars's existing systems. The feedbacks were positive, changes that promoted further change in the same direction, creating runaway dynamics that accelerated decline. Once initiated, the cycle could only be broken by external intervention or exhaustion of the resources driving it. Mars experienced the latter. Eventually, so much atmosphere was lost that storms could no longer achieve their former intensity. This feedback loop eroded habitability. Without a clear breaking point, life, if present, would have faced relentless pressure. Adaptation would have required constant change. Stability, essential for long-term survival, became rare. Any organisms that might have colonized early Mars would have confronted not gradual change, but accelerating instability. Temperature swings intensified. Surface conditions fluctuated wildly between storm and clear periods. Resource availability varied unpredictably. Such conditions favor extinction over adaptation, especially for complex organisms requiring stable environments. Mars lacked the systems needed to interrupt this cycle. No liquid oceans to absorb excess heat. No biosphere to regulate gases. No plate tectonics to refresh the surface. Once storms dominated, there was no escape. The planet had no thermostat, no regulatory mechanism capable of damping the oscillations and restoring equilibrium. Earth possesses multiple negative feedback systems that resist runaway change. Mars had few, if any. The absence of these stabilizing mechanisms meant that once perturbations exceeded certain thresholds, the system could not self-correct, but instead spiraled toward new, more extreme states. The conflict was not between Mars and its storms. It was between endurance and erosion. The storms did not intend to destroy. They simply followed physical laws amplified by imbalance. There was no agency, no purpose, merely physics operating in a system lacking stabilizing constraints. The storms were inevitable consequences of energy imbalances in a thin, unstable atmosphere on a small planet with declining internal heat and weakening magnetic protection. They were not anomalies, but expected outcomes given Mars's circumstances. Over time, these storms reshaped the planet's identity. Mars transitioned from a world of cycles to a world of extremes. Extremes do not favor recovery. They favor collapse. Cyclical systems can maintain themselves through repetition of stable patterns. Systems dominated by extremes lack the regularity necessary for persistence. Mars lost its cycles, diurnal and seasonal patterns that might have supported adapted life, and gained instead chaotic variability that resisted adaptation. This realization challenges how we interpret planetary danger, not as sudden disaster, but as sustained stress. Mars did not fall in a moment. It was worn away by repetition. The lesson applies broadly. Catastrophic change need not arrive dramatically. Incremental degradation under chronic stress can be equally devastating and perhaps more insidious because it occurs slowly enough that each step seems manageable even as the cumulative trajectory leads inexorably toward collapse. The ancient storms were not violent interruptions. They were relentless reminders that stability, once lost, is rarely regained. Systems tend toward equilibrium, but not all equilibria are habitable. Mars found a new stable state. Cold, dry, nearly airless. But achieving that stability required traversing a long period of turbulent transition driven by these persistent storms. The climax of the storm story is the realization that Mars was not destroyed by one overwhelming force. It was reshaped by repetition. Storm after storm, season after season, imbalance became permanent. The cumulative effect of countless individual events exceeded what any single catastrophe could have achieved. This is the power of persistence, that steady, relentless processes can accomplish transformations that momentary extremes cannot. These ancient storms did not just move dust. They moved Mars toward a threshold it could not cross back from. Each cycle stripped away a little more resilience. Each surge made recovery less likely. Eventually, the planet reached a state where calm could no longer return. The transition was not reversible. Mars crossed a point of no return where the systems necessary for atmospheric regeneration no longer functioned. Once past this threshold, the planet's trajectory was fixed, continued thinning toward its present tenuous atmosphere. The resolution of this history is written into the stillness we see today. Mars is quiet not because storms ended, but because there is no longer enough atmosphere to sustain them as they once were. The chaos burned itself out by consuming the conditions that created it. Modern Mars still experiences dust storms, even global ones, but they are pale shadows of the ancient events that reshaped the planet. With less than 1% of Earth's atmospheric pressure, modern Martian winds cannot achieve the sustained intensity of those early storms. The quiet we observe is not peace but exhaustion, the stillness of a system that has run out of energy. What makes this lesson powerful is its subtlety. Mars shows that destruction does not always arrive as a single moment. Sometimes it arrives as endurance, as systems push slightly too far, too often, for too long. The planet demonstrates that catastrophe can be a process rather than an event, unfolding over millions of years through mechanisms that are individually minor but cumulatively overwhelming. The planet did not lose itself to violence. It lost itself to stress without relief. And once that balance was gone, the storms had already done their work. The damage was not instantaneous but incremental, not dramatic but relentless, not obvious but profound. By the time the obvious symptoms appeared, the underlying causes had already run their course. Mars stands as evidence that stability is not lost in a day. It is worn away until nothing remains to stabilize. And by the time silence arrives, the outcome is already sealed. The ancient storms of Mars teach that resilience is finite, that systems can be degraded beyond recovery, and that the transition from habitability to desolation need not be abrupt to be complete. Sometimes the smallest shift in perspective becomes the beginning of a new future. And sometimes that shift is recognizing that gradual decline can be as devastating as sudden catastrophe, that persistence can reshape worlds, and that the storms we survive may matter less than the ones we endure too long.